Hi everyone, welcome back to this video on Bitcoin. Compressed private keys. Ironically, the term compressed private key is a misnomer because when a private key is exported as a WIF compressed, it is actually 1 byte longer than the uncompressed private key. That is because the private key has an added 1 byte suffix shown as 01 in the table 44, which signifies that the private key from the newer wallet should only be used to produce compressed public keys. Private keys are not themselves compressed and cannot be compressed. The term compressed private key really means private key from which only compressed public keys should be derived, whereas uncompressed private key from which only compressed public keys should be derived. You should only refer to the export as WIF compressed or WIF and not refer to the private key itself as compressed to avoid further confusion. Table 44 shows the same key encoded in WIF and WIF compressed formats. Notice that the hex compressed private key format has 1 extra byte at the end, 01 in hex, while the base 58 coding version prefix is the same 0x80 for both WIF and WIF compressed formats. The addition of 1 byte at the end of the number causes the first character of the base 58 encoding to change from 5 to either a K or L. Think of this as base 58 equivalent of decimal encoding, a difference between the number 100 and the number 99. While 100 is 1 digit longer than 99, it also has a prefix of 1 instead of a prefix of 9. As the length changes, it affects the prefix. Base 58, the prefix 5 changes to a K or L as the length of the number increases by 1 byte. Remember, these formats are not used interchangeably. In a newer wallet that implements compressed public keys, the private key will only ever be exported as WIF compressed with a K or L prefix. If the wallet is an older implementation and does not use compressed public keys, the private keys will only ever be exported as WIF with a 5 prefix. The goal here is to signal to the wallet importing these private keys whether it must search the blockchain for compressed or uncompressed public keys and addresses. If a Bitcoin wallet is able to implement compressed public keys, it will use those in all transactions. The private keys in the wallet will be used to derive the public key points on the curve, which will be compressed. The compressed public keys will be used to produce Bitcoin addresses, and those will be used in transactions. When exporting private keys from a new wallet that implements compressed public keys, the WIF is modified with the addition of a 1 byte suffix 01 to the private key. The resulting base 58 check encoded private key is called a compressed WIF and starts with letter K or L instead of starting with a 5, as is the case with WIF encoded non-compressed keys from older wallets. Implementing keys and addresses in Python. The most comprehensive Bitcoin library is Python or PyBitcoin tools by Vitalik Buterin. In example 4.5, we use PyBitcoin tools library imported as Bitcoin to generate and display keys and addresses in various formats. So here you can see example 4.5 key and address generation and formatting with PyBitcoin tools library. So here we go now, it's all there. I'll just go through it again there slowly so you can have a look at it. And here we see example 4.6 running key to address ECC example.py. So there you go. And example 4.7 is another example of Python ECDSA library for the elliptic curve math and without using any specialized Bitcoin libraries. So there it is again, let's go slowly through it for you so you can read it. Example 4.8 shows the output produced by running the script. So here's the output here. So I'll just leave it on the screen there for a minute. Anyone wants to have a look at it? Okay. Advanced keys and addresses. In the following sections we will look at advanced forms of keys and addresses such as encrypted private keys, script multisignature addresses, vanity addresses and paper wallets. Encrypted private keys BIP38. Private keys must remain secret. The need for confidentiality of private keys is a truism that is quite difficult to achieve in practice because it conflicts with the equally important security objective of availability. Keeping the private key private is much harder. You need to store backups of the private key to avoid losing it. A private key stored in a wallet that is encrypted by a password might be secure, but that wallet needs to be backed up. At times, users need to move keys from one wallet to another to upgrade or replace the wallet software. For example, private key backups might also be stored on paper wallets. See paper wallets on page 88, or on external storage media such as a USB flash drive. But what if the backup itself is stolen or lost? These conflicting security goals led to the introduction of a portable and convenient standard for encrypting private keys in a way that can be understood by many different wallets and Bitcoin clients, standardized by BIP38. BIP38 proposes a common standard for encrypting private keys with a passphrase and encoding them with base 58 check so they can be stored securely on backup media, transported securely between wallets, or kept in any other conditions where the key might be exposed. The standard for encryption uses the Advanced Encryption Standard AES, a standard established by the NIST and used broadly in data encryption implementation for commercial and military applications. A BIP38 encryption scheme takes as input a private Bitcoin key, usually encoded in the WIF as a base 58 check string with the prefix of 5. Additionally, the BIP38 encryption scheme takes a passphrase, a long password usually composed of several words, or a complex string of alphanumeric characters. The result of the BIP38 encryption scheme is a base 58 check encoded encrypted private key that begins with the prefix 6p. If you see a key that starts with 6p, it is encrypted and requires a passphrase in order to decrypt it back into a WIF formatted private key prefix 5 that can be used in any wallet. Many wallet applications now recognize BIP38 encrypted private keys and will prompt the user for a passphrase to decrypt and import the key. Third-party applications such as the incredibly useful browser-based bit address wallet details tab can be used to decrypt BIP38 keys. The most common use for BIP38 encrypted keys is for paper wallets that can be used to back up private keys on a piece of paper as long as the user selects a strong passphrase. A paper wallet with BIP38 encrypted private keys is incredibly secure and a great way to create offline Bitcoin storage, also known as cold storage. Test the encrypted keys in table 4.5 using bitaddress.org to see how they get decrypted by entering the passphrase. So here you go, you can do that if you like. Pay to script hash PS2H and multisig addresses. As we know, traditional Bitcoin addresses begin with the number 1 and are derived from the public key, which is derived from the private key. Although anyone can send Bitcoin to one address, that Bitcoin can only be spent by presenting the corresponding private key signature and public key hash. Bitcoin addresses that begin with the number 3 are pay to script hash P2SH addresses, sometimes erroneously called multisignature or multisig addresses. They designate the beneficiary of a Bitcoin transaction as the hash of a script instead of the owner of a public key. The feature was introduced in January 2012 with BIP 16 and is being widely adopted because it provides the opportunity to add functionality to the address itself. Unlike transactions to send funds to traditional 1 Bitcoin addresses, also known as pay to public key hash P2PKH, funds sent to 3 addresses require something more than the presentation of one public key hash and 1 public key signature as proof of ownership. The requirements are designed at the time the address is created within the script, and all inputs to this address will be encumbered with the same requirements. A P2SH address is created from a transaction script which defines who can spend a transaction output. Encoding a P2SH address involves using the same double hash function as used during the creation of a Bitcoin address, only applied on the script instead of the public key. Script hash RIPEND160 SHA256 script. The resulting script hash is encoded with base 58 check with a prefix of 5, which results in an encoded address starting with A3. An example of a P2SH address is 3F6I6 KWKAKEVJ R7ASAD 4TE2YB2ZZYASEM1HM, which can be derived using the Bitcoin Explorer commands script encode SHA256 RIPMD160 and base 58 check encode as follows. Echo dump hash 89 A B C D E F A B B A A B B A A B B A A B B A A B B A A B B A A B B A A B B A equal verify check 6 script SBX encode script BX SHA BX ripe MD16 BX base 58 check encode version 3F6I6 KWKEV J R7ASA D4TE2YB2ZZY ASEM1HM. Multisignature addresses and P2SH. Currently, the most common implementation of the P2SH function is the multi-signature address script. As the name implies, the underlying script requires more than one signature to prove ownership and therefore spend funds. The Bitcoin multi-signature feature is designed to require M signatures, also known as threshold, from a total of N keys known as M of N multisig, where M is equal to or less than N. For example, Bob, the coffee shop owner, could use a multi-signature address requiring one of two signatures from a key belonging to him and a key belonging to his spouse, ensuring either of account as implemented in traditional banking, where either spouse can spend with a single signature. Or GoFet, I suppose, a web designer paid by Bob to create a website might have a 2 of 3 multi-signature address for his business that ensures that no funds can be spent unless 2 of the business partners sign a transaction. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.